Alrighty, good morning, peeps. Alrighty, how you guys doing? Any questions you want to throw my way before we get started?
Yes.
Okay.
Are we going to have another homework before our next test or no?
Yes, I was going to set one up for today. Let's see. That's a good question. Oh, I better turn my clock off. Hang on. Just like being in London, the chimes ring every 15 minutes. Yes, so we're supposed to have an exam on the 24th, right? So if I gave you another homework set now, you see the current one is due Wednesday night, so this next one would be due the following Wednesday night, the 22nd. How does that sound? I'll make myself a note here. The 22nd, and then the exam on the 24th. So yes, Piana, the answer is yes, and I haven't done it yet, but I will. Anything else that you guys need to ask me? All right, do you have some more questions about the homework assignment that you're currently working on, the one that's due Wednesday night? All right, I actually want to do one more example from there, and for a couple of reasons. One is I think it'll give you a little more geometric intuition about how to set up some of these stranger coordinate systems. And also because it's going to lead us into Chapter 7, which is our next topic. Chapter 7 is about integrals that are one-dimensional integrals again, so more like, a little bit more like Calc 2 or something. But since we're going to be integrating over curves, one of the things we have to do is to remember our different ways to present curves. And in particular, one of the ways that we can present a curve is parametrically. That's going to basically be the main way we have to present our curves. And just to get you back in the habit of thinking of parameterizations of curves and of surfaces, which will come next, I want to point out that all of the things we've been doing with the change of variable theorem are actually parameterization questions. So I'm going to do at first a straightforward-ish kind of surface integral that uses the change of variable theorem. And then if I have a few minutes, I'll give you a little bit of a more exotic reminder of how parameterizations work. So I'm going to turn this around, get my document camera back. There. And I got a new light. Oh, that might be too much. All right, we'll see. All right, so one of the examples that you had asked you to compute an integral over a diamond, a square that was tilted, and they told you what the corner points were supposed to be. I think one of them was here, one of them was there, and one of them was here. So if they just tell you the corners of this region, and they tell you that it's supposed to be straight line segments that join them, well, let me put in the coordinates, the Cartesian coordinates of these points. So this is the origin, obviously. This is 1, 2, 2, -1, and 1, 3. Now, from the Cartesian coordinates, you can get the equations of the straight lines that join these things. A couple of them are easy because you just need the slope. The y-intercept is 0. And so, for example, this one would be y equals -1/2 x. For these other two, you'd have to figure out the slope and a y-intercept. But you would discover, actually, that in this case, for example, the y-coordinate is equal to 2 times the x-coordinate -3. Did I do that right?
Should that be 3, 1, Doctor?
Yes, thank you. I was just about to discover that that wasn't going to work. No, so I did this wrong. 3, 2, 4x minus 5, right? 6 minus 1, 6 minus 5 is 1. Yeah, okay. And this one I could also figure it out with the slope y-intercept formula, but allow me to write this one a little differently. Instead of writing y as a function of x, in other words, instead of writing this straight line explicitly, let's write it implicitly. I can write this, for example, as the set of points where 2y plus x is equal to 0. And the reason that I do that is because this other line, one that's parallel to it, I know it'll have the same slope, so there will still be this factor of a minus 2 in front of the x. If I clear things by moving everything to the left-hand side, then the equation for this one will also be 2y plus x equals a constant. The constant has to be different, though. Let's see, 2y's plus x in this case, and in this one, 2y's plus x will add up to 5. So what we see is that both of these edges are sets of points where the function 2y plus x is being held constant. So the way we proceed with the change of variables in this setting is to let this quantity that's staying constant be called u. And then the quantity u varies from 0 to 5. Now, I don't want you to just think about this as a quantity that stays fixed. Rather, what you need to think of is that u becomes a function of x and y that's evaluated at every point in the xy plane. And this curve here is one of the level curves of that function of x and y. This is the set of points where u stays constant. U is equal to 5. In the same way, this is also the set of points where u stays constant. It's just a different constant. And between these are a bunch of intermediate curves, well, they happen to be straight lines in our case, where the function u takes on different values that are between 0 and 5. In the same way, I wrote these two straight lines explicitly, but it's actually a little bit easier to deal with what I'm about to do if I get used to writing those straight lines implicitly. In other words, think of them as a set of points where something stays constant. And the something I have in mind would be y minus 2x. That's equal to 0 on this end, and it's equal to, I guess, -5. Oops, sorry, y minus 2x is equal to -5 on this end. So now I have a different something that's staying constant on the two other edges of this region. I'm thinking about this now as being a new quantity, a new function defined on x and y that I'm calling v. And these two straight lines are now level sets for the function y. They're level curves. Well, they happen to be straight lines, but those are two of the lines on which the function v stays constant. And of course, there's other lines where v takes on other values. V is equal to -5 here. It might be -4 somewhere up here. V is equal to 0 there. So on the one hand, you started off with this region drawn in the xy plane, but you really need to think about the diamond as just existing in some, I don't know, some platonic universe just all by itself, where it doesn't necessarily have Cartesian coordinates drawn around it. You can draw Cartesian coordinates around it and then assign x and y coordinates for each one of these points. But numbers x and y themselves are just two functions that you evaluate at each point. At this point, well, at any point, the thing we call the x coordinate is really just a function that measures how far you are from this line. It's this distance. That's what the number 1 represents. So it's a function that you define at each one of these points. You have a function that's defined on this diamond, and for every point on the diamond, it just gives you a real number. That's what the x-coordinate is. The y-coordinate does something similar. But now you should recognize that the u and v coordinates also are just functions that are defined at each point on the diamond, spitting out, for each point of these points, it evaluates something somehow, and it creates a real number. So they're functions defined on the diamond. In fact, they're defined on the entire plane, and they just report numbers, 4 different numbers that you can report for each point on the plane. I know that the region has been given to you in x and y coordinates. That's the way that it's perhaps easiest to visualize it first, but it's not the only way that you can present these points. I mean, I can ask you where the point is that has an x-coordinate of 2 and a y-coordinate of 1. That would be, I first have to, well, let me do that over here. To find the point that has an x-coordinate of 2, I look at all the points where an x-coordinate is equal to 2, and I look at all the points where the y-coordinate is equal to 1, and I say, well, if you want the x-coordinate to be 2 and the y-coordinate to be 1, that means you have to lie on both of those lines, and there's only one point of intersection of those two lines, so I know exactly what point I'm talking about. I can draw it now. In the same way, I could say, well, what about, where would you find the point whose u-coordinate is 2 and whose v-coordinate is -1? Well, across the entire plane, I can draw all the points that have a u-coordinate of 2, and I could draw all the points whose v-coordinate is -1, and each one of those would also be a straight line, and the intersection of those two lines is just a single point. So here's the point where x is equal to 2 and y is equal to 1. Here's the point where u is equal to 2 and v is equal to, I think I said -1. If you ask me, like, where is the point, in both cases I've just shown it to you. Somehow we're more used to Cartesian coordinates, and so you think I've told you where the point is in here, whereas it feels like I haven't told you where the point is in this case. I have, I mean, I've drawn it for you, but the problem is for a lot of students, it doesn't feel like I've told you where it is because the graph paper that you're drawing this on doesn't have this set of lines and that set of lines drawn on it in some sort of native way. Your graph paper might have these lines where x is constant, and those lines where y is constant. They may already be pre-drawn on your paper. If you really want to know what the x and y coordinates are for this point, I can get them for you because we have a system for changing the coordinates back and forth from x and y to u and v, or from u and v to x and y. I can do it either way. The way that's easier, because of the way that I started the problem, is the description that tells me how to get the u and v coordinates from the x and y. But of course, I can do it both ways. The formulas that give me u and v in terms of x and y are these two. But I can think of this as two equations and two unknowns that I could then solve for unknown x and y coordinates. That pair of equations would tell me how to compute x and y from u and v. Let's see, I think we did this last time, I can't remember exactly, but if I double this equation and I add it to this equation, then all the x's will disappear. I'll have a total of 5 y's, and on this side I'll get 2u plus v. So y would be 2u plus v over 5. And in the same way I can solve for x, I can eliminate the y's to get an equation that has only x's in it. Take this top equation minus 2 of the bottom. In other words, compute u minus 2v. Then you'll see that you have 5 x's left alone on this side of the equation. So x can be computed in this way. So the way that I was setting these kinds of problems up for you last time was to say, oh, well, you've already been given this region, this diamond in the xy plane. And so your job now is to write this as the image of something in the UV plane. I better label my axes here. You needed to find the combinations of u's and v's that map onto this. So somehow I was giving preference to the Cartesian coordinates and thinking of these as newly introduced coordinates. But these two formulas actually work both ways, and on some level there's no reason to prefer one over the other one. This is the one that I will use in my integration formula, the change of variable theorem. I'll show you why in a second. But I could just as well be discussing the one that goes in the opposite direction to show that on some level, neither the u and v coordinates nor the x and y coordinates is innately more preferable. So let's see, my formulas that take a point with u and v coordinates and spit out a point with x and y coordinates is this one. So t of u comma v is equal to u minus 2v over 5. I'll just write the same formula again. I'm not sure why I'm doing this. 2u plus v over 5. And the opposite formula takes the x and y coordinates and gives you the u and v coordinates. That's this one up here. I'll just call it w and t. Now, because these are linear formulas, it's pretty easy to figure out exactly the range of u's and v's that correspond to the points that are in the diamond. You know that for a linear function where you have no u squareds or u times v or anything, a linear function that goes from one coordinate system to the other one is also going to take straight lines to straight lines. So if I can just figure out where each of these four corners go in this other picture, then since there are straight lines that join them in this picture, there will be straight lines that join them in that picture. Well, that's easy enough to do. I was told in the beginning the x and y coordinates of these different points. This point, for example, has x equals 1 and y equals 2. Well, if you know the x and the y coordinates, so then you can get the u and v coordinates. If x equals 1 and y equals 2, then the u coordinate is 5. And if x is 1 and y is 2, then the v coordinate is 0. So this point here maps to this point here. Likewise, if I know the x and the y coordinates, I can just use the formula for w. And let's see, if y is 1 and x is 3, this will come out to be a 5 again. But now if y is 1 and x is 3, 1 minus 6 is negative 5. So I'm down here. Now let me pause for a second on this point to show you something else you could do, and some students find this to be easier, is to say, look, I need to know the u and the v coordinates that got me to this point. And so you could be saying, well, look, if I know the x and the y coordinates, sometimes the x and y coordinates are given to you in terms of the new coordinates, the u and the v. That's exactly the situation you're in when you talk about a switch to polar coordinates. In a polar coordinate system, it's usually easier, it's more natural to have these formulas that express the x and the y in terms of the u and the v, or the r and the theta. So sometimes the function capital T is the one that's easier to deal with. And it's the one that we actually need in the change of variable theorem, but it makes it a bit more awkward to get coordinates of points like this. So a minute ago, I got the coordinates of this point B, the u and v coordinates of this point B, by using the formula for capital W, the one that actually computes u and v coordinates from x and y coordinates. But if all you have, or if the more natural one for you to have is the t function, that changes u's and v's into x's and y's, then you would have to play a game like this. You'd have to say, well, if I want the u and v coordinates of this point, I have to start with what I know my x and y coordinates are, and then compare them to these formulas to say now the two coordinates that are unknown are the u and v coordinates. And so I have to think of these as two equations in the two unknowns, u and v. Well, two equations and two unknowns, I know how to solve those. We'll clear away some 5s, eliminate u's or v's, and eventually you'll discover the u and v coordinates that I had before. The point B has a u coordinate of 5 and a v coordinate of -5. So I guess what I'm trying to say is that you have ways of going back and forth, and there's no particular reason that you need to think of the Cartesian coordinates as in any way more natural, that somehow the diamond is there first, out before any coordinates are drawn. You can describe it with x and y coordinates, describe all the points with their x and y coordinates. You can describe all the points with their u and v coordinates. You can even, if you wish, put both coordinate systems into the same picture, and that's what I've done here. Here's the diamond. You can imagine the diamond was just floating in space somehow before we entered the picture, and then somebody latched onto it and drew a pair of axes here and declared that they would be the x and y axes, and then started measuring off those sets of points where x or y would stay constant and measured the x and y coordinates of the point. And meanwhile, somebody else jumps in and starts marking off the sets of points where u and v coordinates stay constant, and then they declare the u and v coordinates of each of these points. So, you know, in both cases, what you're doing is parameterizing the diamond. You're telling how to get to all the different points in the diamond, how to distinguish one point in the diamond from another point by reporting a pair of numbers. That pair of numbers can be the x and y coordinate, or it can be the u and the v coordinate. So we've been discussing this from the perspective of the change of variable theorem, but we're going to be shifting to thinking about this in the sense of parameterizing a surface with our choice of coordinates. Yes, I know that the original picture was given in terms of x's and y's, but on some basic level, some like philosophical level, you can think of either coordinate system as being appropriately natural. Now, I did say why we have the function t floating around and not the function w in the change of variable theorem. The reason for that is that what we're trying to do with this diamond is integrate some function on it. I actually don't remember what function you had to integrate in the homework on this diamond, but what on some level you were doing was drawing another arrow. This one only goes in one direction, and it maps onto the real number line. And so that was a function that takes in these various points, and it measures a number at every one of those. Of course, in order for me to give you that function, somehow I have to give you a mechanism that would allow you to take a point and do some computations with it to get the number that I'm trying to describe over here. If probably the easiest way to do that, of course, is to set up a coordinate system and then write out a formula for how to compute that function from those two coordinates you've chosen. So if I say, for example, that I want you to integrate the function x plus y on this diamond, well, that means I'm asking you to take every point in here, first compute its x and y coordinates by dropping perpendiculars to the axes and measuring those lengths. That number is called x, that number is called y, and then adding those lengths for whatever reason. That's how I would get a number. Well, as you can see, I've just given some preference to Cartesian coordinates. I can still express the values of the function at every point by going to the image of that diamond over here, finding out where that point is in this picture. Let's see, it's closer to B than it is to A. It's over here somewhere. And so I could look at its u and v coordinates, and then I'd have to give you a recipe for how to compute the values of this same function in terms of u and v coordinates. Well, if the function was previously given to you in terms of x and y coordinates, then you've got the function defined on the xy plane. And so evaluating the function straight in this direction amounts to taking the point from knowing its u and v coordinates, transferring those with this function t to get x and y coordinates, and then using the formula for f that took in the x and y coordinates to actually evaluate the function. So the preference has become for Cartesian coordinates just because that's how the original function was defined that I'm supposed to integrate. But in both cases, I have this idea that I'm going to evaluate the integral of this function f over this diamond. It's still the same idea that it always has been in every one of our integration problems. You're going to take this, break it up into little parts, and evaluate the function at one point within each part, and then multiply the value of the function times the size of the part, and then add them up. Of course, when you've got the Cartesian plane floating around, nobody would break up the diamond into shapes like this. They would break it up into little segments, little squares whose sides are parallel to the axes. And then when you measure the area element is just the change in the u coordinate times, the change in the x coordinate times the change in the y coordinate. That gives you the area of each little piece. You can measure the same thing in this picture. Again, if you think about the diamond as having been there before the coordinate system, then it's a perfectly reasonable thing. In fact, a more natural thing to split this diamond up into a bunch of, well, smaller diamonds. And then you could evaluate the function at some point within each one of those little pieces. And then you have to multiply by the size of the region that's the size of this little piece of the original diamond. Now the problem is the way I put my lines into this figure, the slanted lines, if I take the region that's between, let's say, the line v equals -4 and the line v equals -5, and over here I take the region that's between the lines u equals 2 and u equals 3, I've gone a distance of 1 in each of the directions u and v, but I've shown you a diamond whose area isn't one square unit. It's not one square unit of area in the x and y sense. So unfortunately for the u and v coordinates, we're not measuring areas by simply taking du times dv. It's not the lengths of those two sides. It's the length of those two sides times this determinant of this t prime, the absolute value of the determinant of t prime, because that determinant, that Jacobian determinant, measures how much this function capital T shifts areas when you move from this coordinate system to that coordinate system. In this particular case, where's T? In this particular case, we can figure out the Jacobian determinant pretty fast. It's just a bunch of numbers. We don't have functions of u and v in this case. Here's the partial with respect to u, partial with respect to v. Let's see, u, so 2/5 here and 1/5 here. Then the determinant of t prime, I get 1/5 plus 4/5, 1/25 plus 4/25, which is 1/5. And what this tells us is that this function t is near every point, it's reducing areas by a factor of 5. And I think maybe you can see that this little square has a total area of 25. Whereas this square, I'll let you figure out the length of the side. It turns out to be square root of 5. Yes, square root of 5. So a square whose side has a length square root of 5. This one has an area of just 5. And so areas have been reduced by a factor of 5 in here. So the problem is given to you usually with Cartesian coordinates just because that's a handy way for us to describe a function. And the Cartesian coordinates are the ones that usually are used to describe how you compute areas. I meant when I compute an area, I mean, well, areas in square whatevers, where whatever is the unit of length that I'm using for the x and the y coordinates. So there's like two preferences given to the Cartesian coordinate system. But on some intrinsic level, these are just two different ways of parameterizing the diamond that exists. You can draw a diamond without having any coordinate system at all. All right.
Drusen?
Yes, go ahead.
I have a question. Why does the determinant measure like the amount of the area changes? Like,
that's a good question. Yeah, that's a good question, and it's really kind of hard to answer until you do a linear algebra class. There are a couple of cases where it is easy to illustrate why the determinant is measuring the right thing, but in general, it's a little bit hard. Let me just show you an example like this. Suppose that I have a function capital T that takes in the u and v coordinates, and it simply doubles the u coordinate and triples the v coordinate to get the x and the y coordinates. So what does that linear transformation do to areas? Well, let's take a sample region in the UV plane and see what happens to it in the XY plane. So if I take the square that goes from 0, 0 up to 1, 1, and of course 0, 1 and 1, 0 are the other two corners, you know that I've gone 1 unit in each direction, and so in the UV plane, the area of this little square is 1. What's its image when I apply the function capital T to all the points whose u and v coordinates are both between 0 and 1? Well, obviously what's going to happen here is your x coordinate will take on all the values between 0 and 2, and independently, so no matter what x coordinate you've just chosen, your y coordinate will be somewhere between 0 and 3. So now it's clear that the image of this square in the xy plane will be a rectangle that's 2 units on the horizontal axis and 3 units on the vertical axis, and so the area of this one is a 6. And more generally, I think you can see there's nothing special about the numbers 2 and 3. If you put any constants here, a and b, then you'll be stretching by a factor of a in the horizontal direction and stretching by a factor of b in the vertical direction. I don't want to call it y or v, but the v's get multiplied by a factor of b to give you the y's, and likewise u's and x's. And when you do that, a square here changes into a rectangle here, but the length of the horizontal has been magnified by that factor, and the length of the vertical has been magnified by this factor. So the total change of the area is always going to be that areas will be multiplied by a factor of a times b. Now, if you write down the 2 by 2 matrix that corresponds to this transformation, that'll be always a diagonal matrix. Here it is for our particular case. 2u and 3v gives me this derivative matrix. But in the more general case, if I put an a and a b there, I'll just have an a and a b here. So at least in the case of a diagonal matrix, I think it's clear when you trace through what happens to the unit square, I think it's clear that it's the determinant, which happens to be a times b as well. The determinant is measuring what happens to the areas. Yeah?
Yeah, that makes sense. But like, this just for this example, because there's
correct.
Zeros.
Correct, yeah. So let me give you another example that doesn't have zeros in it. And then I'll also be able to make a similar claim. So this time I'm going to take t of u comma v is equal to u plus 2v comma v. So now let's see what happens to the unit square in this case. So again, I have u and v coordinates that go between 0 and 1 independently of each other. And in this case, I've started off with an area of 1. Area equals 1. I apply this transformation t, and I'm going to get something in the xy plane, but it won't be a square this time. It won't even be a rectangle. Oops, sorry, x and y. So what do we know? Well, your v coordinates are this, your y coordinates will be the same as the v coordinates, so they'll just range from 0 to 1. In fact, if you try to trace out where you're going to end up in the xy plane, when you start with a point in the uv plane, the y coordinate will be the same as the v coordinate, so whichever horizontal line you were in over here, these are the set of points that have a particular v coordinate. Well, all those points will have the same y coordinate. So every point that's on this line segment will just be shifted to somewhere else in this, on this horizontal line. But where exactly are they going to go? Oops, sorry. Well, what will happen is, based on how high you were, you're going to shift, your x-coordinate will be shifted from your u-coordinate. For points that had a v-coordinate equal to 0, those were the points on the bottom edge. All the points that had a v-coordinate of 0 will have an x-coordinate that's the same as their u-coordinate. However far you were from left to right before, you'll be exactly as far left or right in this picture. And in particular, you'll have x-coordinates that only vary between 0 and 1. The origin will get sent here. This point over here, should I call it capital A again? That'll get sent to this point over here. But if you think about the points that are in one of these other horizontal line segments, they'll be shifted into a horizontal line segment again, but it won't be just directly, it won't just stay put. For example, if I look at all the points that are up here at the top, when their v coordinate is 2, you can see that the x coordinate will just be u plus 2. Every point that's over here, somewhere with a u coordinate between 0 and 1, those points will be given an x coordinate that's between 2 and 3. So they'll be shifted all the way over here. So in particular, this point will be shifted to this one. This is the point whose u and v coordinates are 0 and 1. 0 and 1 will be sent to 2, 1, which is over here. And of course, that point is sent there. I'll let you work out the arithmetic. And more generally, what you see happening from this line segment and that line segment, this one and this one, is that one of these line segments that has all the points with a fixed v coordinate, they'll all be shifted by a fixed amount. Their x coordinate will be shifted from the u coordinate by adding in a constant value. And that constant value is actually going to turn this line segment into a line segment over here that'll have a slope of, I guess that's a slope of 2. And this other one, all of these points, I'll let you do the computation there. It'll give you these. In fact, let me take the word, since I've started to use the word parameterize a lot, I'm getting you guys ready for chapter 7. This line segment is part of a line that you would get by applying this transformation to all the points in this line. These are all the points that have u equal to 1. And if you stick u equal to 1 into this formula, you see that you're getting x equal to 1 plus 2v, y equal to v. So this pair of formulas parameterizes a line in the xy plane. The name of the parameter is v, and as v varies from 0 to 1, I get all the points from A to C. I'll get all the points along this straight line. All right, so I spent a lot of time trying to show you what this transformation does. Now I'm going to ask you 2 questions. What would you get for the determinant of t prime in this case? And how do you think that areas are changing in this case? So which one of these should we do first? Maybe the determinant one is easier because it's just a bunch of computation. Let's see, where'd it go? To find the derivative of this function of u and v, I'll differentiate x with respect to u and v, differentiate y with respect to u and v, and there's my matrix. And I guess while I've got the matrix handy, let me point out that the determinant is equal to 1. Now, how do we get the area of a, what is this, a trapezoid?
Base times the height.
It's base times the height. And remember, height means you go up in a direction that's perpendicular from the edge that you call the base. So if you think of this as the base, that's obviously base times height is correct. And the base is of length 1. to measure the height, I don't need that length of that slanted line. What I need is how far did you go up this way? There's your h. And you know what I said earlier, that I just took all these points on a certain horizontal line and I kept them along that horizontal line. So if this height was 1 before, it's still a height of 1. So the area is exactly a 1. And that would be true no matter what this number 2 is. The 2 just tells you how much of a shifting you're doing that way. It's not a rotation, by the way. You need to think about a whole deck of cards that somebody has tapped from the side to scoot the cards over. You're looking edge on at the deck of cards. So the deck of cards has still got the same height. It's just that the top card is scooted over from the bottom one. No matter how far you scoot it, the total area of the cross section in the back, it hasn't changed. So the area is always going to be a 1. Now, at this moment, I'm going to whip out a linear algebra fact. When you compute the determinant of a linear transformation, the determinant of a product of matrices is the product of the determinants of the individual matrices. That's one piece of information you need from a linear algebra class. A second one that you need is that every linear transformation can be written as a composition of functions like this, I don't know what to call this one for you guys, this scooting over, and the ones that I had before. So there is a process that you run through in a linear algebra course called diagonalization, and it teaches you that, well, with a few exceptions, and you have to interpret things the right way, basically every linear transformation can be written as a product of a diagonal matrix with some matrices that look like this on the left and the right side. You take products of matrices that just do these things and matrices that do these things. If you know anything about row reduction of a matrix, you know that you can take a matrix and row reduce it by running through a sequence of operations that say, let's add a multiple of one row to another row, or let's scale up one of the rows by a constant. You are, in effect, writing every matrix as a product of matrices of these two simple types. So you got to figure that you're going through a sequence of manipulations to transform every linear transformation. Every one of the things that goes from here to here is accomplished by a few of these funny little twists and stretchings, but it's only the stretchings that actually change the area. So if the determinant is the product of the determinants of the various pieces, and the area is also being changed by a sequence of area manipulations, if they're sort of mimicking each other step by step, and all of your steps involve only this kind of a change and this kind of a change, then sort of the two of them are working in parallel. The changes in the area are always going to match the value of the determinant. So I know that that was a lot of words going by really fast. Essentially what I did was I just gave you about 3 weeks of a linear algebra class rolled into one. But at least I hope you see with a couple of these examples why the determinant is at least capturing, in some simple examples, it's capturing what the change in the area is.
And it works if the transformation isn't linear? Like, because the examples you gave are all linear, right?
Yes, but okay, that's a good question too. And that takes us back away from the linear algebra class back into our class. But that has to do with the reason why we put derivatives in there in the first place. So let me just take this example of polar coordinates. So remember, the formula for polar coordinates uses this transformation t. Polar is one of the cases where it's easier to give the x and y in terms of the u and the v instead of the other way around. That'll be handy for us. So there's your transformation. Where, for example, does this function take the point when r is equal to 1 and theta is equal to pi over 4? Answer, well, I'll just plug these numbers in and I get the x coordinate is equal to 1 over root 2 and the y coordinate is 1 over root 2. Okay, cool. Now, where does it take a little region around that pair of numbers in the r theta plane? So let's find that point first. Here's r, here's theta, and here's r equals 1. Here's theta equals pi over 4. So there's this one point. All the points nearby have r coordinates that are close to 1 and theta coordinates that are close to pi over 4. I could ask you to take particular values. I could take the little rectangle that goes from, let's say, r equals 0.9 to r equals 1.1. So that's got a width in the r direction of 0.2. And likewise over here, I'm going to give you some specific numbers. See, pi is 3.14, so if you divide that by 4, you get 0.78 something. So how about if I go from theta equals 0.75 on this end to theta equals 0.8, oops, 0.8 on that end. So there's a little region around that one point, and it's a rectangle in our theta space. When you apply the transformation t, you're going to get a point that's near this point. Here's 1 over root 2 is about 0.7. Here's 1. Here's 0.7. So there's the point that this guy is being sent to. And this little rectangle will be sent to a region that's near here. You know it's not a rectangle. In fact, it doesn't have straight sides. 2 of the sides are not even straight. They're portions of a circle. Here's the circle of radius 1.1. Here's the circle of radius 0.9. And then you have those lines where theta is equal to 0.75 and theta is equal to 0.8. Those are 2 lines that come out of the origin. So how the heck am I supposed to get the area of this region? Well, you could actually figure it out because you know how to calculate the area of a sector of a circle, and you know how to get the area of if you subtract 2 such sectors, you take the area of this kind of triangular thing minus the area of an inner one, and that would give you this area. But rather than actually calculate that area using some high school formulas, what you might think to do is to say, well, look, approximately speaking, I can figure out where the corners of these of this little rectangle went. I can figure out where approximately these 4 points are, and then I could replace those 4 edges not by these curves, but by straight lines that join them. Same thing with this line and this line. There's a curve here, I replace that with a straight line. And what do I mean when I say approximately? Well, look, this point up here has coordinates of r equals 1.1 and theta equals 0.8, right? Okay, take those numbers and shove them into this formula. What's that? You don't want to compute the cosine of 0.8? Not a problem, because you are actually asking me at this moment to estimate approximately where this point gets transferred to in Cartesian coordinates. I would say that this point is 1 plus a small movement in the r direction. This point here is pi over 4 plus a small movement in the theta direction. I don't know what this amount is, 0.02 apparently. And then what a derivative does for you is it says, look, if you want to calculate t of this thing, we did this earlier in the semester. This is going to be the same as t of the central point plus, and now you're supposed to take exactly this derivative, evaluate it at the center point of this little figure, and multiply that 2 by 2 matrix by the numbers 0.1 and 0.02. That's what we did with derivatives all early in the semester. We used derivatives precisely so that we could estimate, should be an estimate where points go that are nearby to a nice point. We know the nice point is sent right to here. So from here, how far do I need to go left and right to get to this point? How far do I need to go up and down? That will be a vector that I get by multiplying this vector by this 2 by 2 matrix. And this is the 2 by 2 matrix that I've computed for you a number of times. It's cosine of theta, r sine of theta, minus r sine of theta, sine of theta, cosine, r cosine of theta. And when you evaluate this matrix at the point 1 comma pi over 4, you get this matrix of numbers minus 1 over root 2, 1 over root 2. And you multiply that matrix times this small vector. That's the small vector that joins these 2 points. That vector gets transformed in this picture to give you a small vector in the xy plane. It won't tell me exactly where t of 1.1 comma 0.8 is, but it'll point to something that's nearby. And I'm going to replace all 4 of these corner points by something else that's nearby, and then look at the rectangle that I get that joins those. The area of that rectangle will be almost the same as the area of this little wedge of the circle. So that's the point of the derivative. The derivative is allowing you to just replace tiny little regions in the r theta plane with nice rectangular regions in the xy plane. And those rectangular areas are now the ones that are computed by multiplying you get the areas by multiplying by a determinant. Okay, so the reason the derivative is involved is that's like the first step that replaces a non-rectangular region in the xy plane by a rectangular region. We're using the derivative as the best linear approximation to the original function near a particular point. And then we're using the determinant to say, oh, well, then how much does that linear transformation affect areas?
Okay.
It's a subtle question. I really didn't expect anybody to want me to go into the details, but since you did, I gave you the answer. And I'm glad you did, actually. I would like the rest of you guys to have a sense of why the derivative is in there. All right, listen, I didn't start chapter 7 with you guys today. I kind of wanted to, but that's okay. This was a good set of questions. So we'll pick up on that next time. But what I do want you to have as a takeaway from all of this stuff is what I was saying earlier, is that you have a region of space, and the x and y coordinates give you one way to determine where you are. The u and v coordinates give you a different way to determine where you are. In each case, you're specifying a pair of numbers to parameterize the points on that surface. The x and y coordinates or the u and the v coordinates are both giving you ways of determining your position within a set. That's a parameterization of a set. We've done it for curves, we're doing it for surfaces, and we're going to need both of those ideas of parameterizing when we do our integrals in chapter 7. Okay? So if you haven't thought about parameterizations in a long time, go back and review those. Think of how you're going to take curves that are given to you explicitly or implicitly and rewrite them so that you have a parameterization of the curves, or I know surfaces are harder, but we'll do those too. Okay? Alrighty, guys. I think with that, we'll call it for today. Hey, try to make sure you can finish up the questions on the homework. Wednesday, we'll have a little bit of time. If there's anything left over, I'll try to get you that. And use the Piazza thing to get help on the homework questions too. That's what it's for. Alrighty, guys. I'll see you on Wednesday.